In this unit, we'll learn how apps running on different hosts can talk to each other. As noted in previous units, a process is a program, that is a code, which is running on a host and requires memory and processing time. We'll distinguish between two types of processes that talk to each other. The first case is that two processes run on the same host. In this case, they can pass data between them in a method called IPC, Inter-Process Communication. This method is within the operating system. We'll stick to that method less because we'll want to look at communication between two processes in the context of computer networks. That is, the two processes will run on different hosts. This is the second case. Two processes running on different hosts have to send and receive messages from each other. There are two common processes in the world of communication: a client process, which initiates connection and requests a service, and a server process, which waits for connection from a client to provide a service. Note that server and client are not computers or hardware at all, but processes. The processes running on them define their rules. In the case of a peer-to-peer network, which we'll learn about in this unit, the hosts run a combination of the two, that is, client processes and server processes in parallel. The processes send and receive messages between each other by using a socket. A socket is a kind of virtual logical plug in the host. You can make the analogy of a socket to a door to a connected host, to which you can send information and from which you can receive information. The doors between the end hosts are synchronized so that any information sent through the first door shows up behind the second door and vice versa. All we have to do is open the doors on each side to view the information. The formal definition of a socket is an endpoint for the flow of data in communication between processes on a computer network. Today, most computer communication is based on socket communication. A software developer doesn't need to program the sockets, but can use them, and they are provided via the operating system. The developer can control them through convenient interfaces. As we know, every host has an IP address by which it can be identified and reached. But because every host may be running several processes, sending and receiving data in parallel, the processes have to be identified too, so that the desired process would take information from the socket so that it wouldn't be taken over by another process. The identification of the running process is done with a special number called a port number. The port number is 16 bits. That is to say, there are a total of 65,536 ports. The port numbers are attached to processes running on hosts. We aren't talking about hardware coming or going, but about a logical number assigned to a process. The running logic is that if a process works with port X and the host received data intended for that port, the process will get the data. Whereas a parallel process in the same host working with port Y will get data sent to port Y, even if it's on the same host. This allows us to differentiate data intended for different processes. You can think of it this way. Using the IP address, the data reaches the correct host. But the ports ensure the data reaches the correct process running on that correct host. The combination of the two is therefore necessary. When the server is running, it runs a server-side process, which sits on a specific port. The client connecting to it needs to know beforehand which port the server is running. So how does a client know what port number to send to the server? The answer is that there is a list of set ports for specific services. It is conventional to work with them. For example, if a client connects to a server serving a website, the client will connect to a port whose number is 80. If the server is an email server, the client will be routed to port 25. There is a long list of port role combinations. On the other hand, the client can work with any port because in any case it will report to the server about its IP address and the port number it works with, so that the server can return the service to the proper address, combined with the right port. In many cases, the client simply allots itself a port, which is free, and doesn't conflict with a process running on the host. We've seen a few protocols on the application layer, such as the File Sharing FTP protocol, HTTP protocol for websites and Internet objects, and SMTP protocol for email. As we know, network protocols are a collection of rules of behaviors between hosts. Each protocol, belonging to a layer in the layer model, defines a role within the layer. The application layer needs to define the communication type, whether it is a frequent communication request or any other kind. The layer has to define the structure of every message. That is the role of every field in the message. For example, field 1 is the origin's IP address, and field 5 is the port address of the destination, and so on. The layer has to define the order, magnitude, and meaning of each field. Additionally, we have to define when each host sends and receives information and the synchronization between them. All these and more are defined by protocols. There are two kinds of protocols. An open protocol, which is open to be used by the developer community and defined by standards organizations. An example of such protocols is SMTP, HTTP, FTP, and so on. On the other hand, there are protocols which are under copyright, such as the Skype protocol. In this unit, we learned about processes in the context of communication networks and specifically client-side and server-side processes. We learned what a socket and a port number are, and defined the details that define a protocol.